Hello, everyone, and welcome. Today we're diving into topic 4, statistics and probability. Specifically, we'll be focusing on a very important concept called regression. By the end of this lesson, you will be able to understand what regression is, how to visualize data using a scatter plot, and how to interpret the relationship between two variables. In many real-world scenarios, we collect data in pairs. For instance, we might measure a student's hours of study and their corresponding exam score. This is called paired data. We have a list of these paired data points. Let's look at an example. Here we have a set of x values and a corresponding set of y values. We typically assume that one variable depends on the other. In our case, we'll assume that x is the independent variable and y is the dependent variable. This means we think the value of y depends on the value of x. Now, just looking at this table of numbers can be a bit abstract. A great way to visualize the relationship between x and y is to plot these points on a graph. This type of graph is called a scatter diagram or a scatter plot. Let's plot our points. We put the x values on the horizontal axis and the y values on the vertical axis. As you can see, when we plot the points, a pattern starts to emerge. It looks like as x increases, y also tends to increase. This leads us to the main question in regression analysis. The key question we want to answer is there a linear relationship between the values of x and the corresponding values of y? In other words, do the points on our scatter plot seem to follow a straight line? To quantify the strength and direction of this linear relationship, we use a special parameter. This parameter is called the correlation coefficient, and it's denoted by the letter R. It's also formally known as Pearson's product moment correlation coefficient. The value of R always falls between -1 and +1 inclusive. This range gives us a standardized way to measure the relationship. The value of R tells us two things: the direction and the strength of the linear relationship. If R is close to +1, it implies a strong positive linear relationship, meaning as x increases, y increases. If R is close to -1, it implies a strong negative linear relationship where y decreases as x increases. And if R is close to 0, it suggests a very weak linear relationship or no linear relationship at all. When the data does show a linear trend, we can model it with a line. There is a line that best fits our data, known as the regression line. Its equation is in the familiar form y equals ax plus b. This line is the best possible straight-line summary of the relationship between our variables. In our next segment, we'll see how to easily find the values of R, A, and B using a calculator. So to recap, we've learned that regression helps us analyze the linear relationship between two variables using scatter plots and the correlation coefficient. Welcome back. In this scene, our goal is to learn how to use a graphing display calculator, or GDC, to find the regression line and correlation coefficient for our dataset. We'll be using the data from our previous example. Manually calculating these values is quite complex, so we rely on technology to do the heavy lifting. The steps can vary slightly between calculator models, but the general process is very similar. Let's look at the steps for a common model, the Casio CFX. First, you'll go into the Statistics menu. You'll see columns for lists. You need to carefully enter all the x values into list 1 and the corresponding y values into list 2. It's crucial that the pairs line up correctly. Once the data is entered, you'll go to the Calculation menu. From there, you select Reg for regression, then X because our equation is in terms of x, and finally ax plus b to specify a linear model. After you select this, the calculator will display the values for A, B, and the correlation coefficient R. Let's see the results for the example data we've been working with. The calculator gives us R equals 0.99. Since this is very close to 1, it confirms our initial observation from the scatter plot. There is a very strong positive correlation between x and y. The calculator also gives us the coefficients for our regression line. We find that A is 9.83 and B is 23.1. So the equation of the regression line that best fits our data is y equals 9.83x plus 23.1. Let's visualize this. We can draw this line on our original scatter plot. As you can see, the line passes through the middle of the points, capturing the overall trend. It's a visual representation of our line of best fit. So we've successfully used our GDC to quantify the relationship we observed. We found a strong positive correlation, and the specific equation for the line that models this relationship. This process is a fundamental tool in statistics. Now that we have our regression line, what can we do with it? In this section, our objective is to learn how to use the regression line to make predictions and to understand the important difference between interpolation and extrapolation. The primary use of a regression line is to predict the value of the dependent variable y for a given value of the independent variable x. We'll use our equation y equals 9.83x plus 23.1 to do this. It's as simple as plugging in a value for x and calculating y. Let's try an example. What if we want to estimate the value of y when x is 18? We substitute 18 for x in our equation. This gives us 9.83 times 18 plus 23.1, which calculates to approximately 200. Now, let's consider the x value we used. Our original data for x ranged from 10 to 30. Since 18 is within this range, this type of prediction is called interpolation. We are estimating a value within the bounds of our observed data. What if we want to predict y for an x value far outside our data range, say x equals 40? We do the same calculation, 9.83 times 40 plus 23.1, which gives us about 416. Because 40 is outside our original data range, this prediction is called extrapolation. We are estimating a value beyond the bounds of our observed data. This distinction is very important. In general, interpolations are considered more reliable than extrapolations. We are more confident in predictions made within the scope of our data. Extrapolating too far assumes the linear trend continues indefinitely, which may not be true in reality. One final crucial point. What if you want to predict x from a given y? It's a common mistake to just take the equation y equals ax plus b and solve for x. This is incorrect. The regression line of y on x is calculated to minimize vertical errors. To predict x from y, you need to minimize horizontal errors, which results in a different line, the regression line of x on y. Your GDC can calculate this for you. For our data, the correct line to predict x from y is x equals 0.0997y minus 1.92. Always use the correct regression line for your prediction. To summarize, we've seen how to use our regression line to make predictions, and we've learned the critical difference between the more reliable interpolation and the less reliable extrapolation. Hello again. In this scene, we will explore two key characteristics of the regression line and then look closer at how to interpret the correlation coefficient, R. These concepts will deepen our understanding of what the regression analysis is actually telling us. Let's start with the regression line. It has some very specific mathematical properties. First, and most importantly, the regression line always passes through a specific point. This point is the mean point, M, whose coordinates are x bar and y bar, representing the mean of the x values and the mean of the y values, respectively. The regression line is essentially anchored by the center of our data cloud. We can find these mean values easily with our GDC. In the stat mode, after entering your data, you can select two variable statistics, and the calculator will provide a list of statistics for both x and y, including their means. For our running example, the mean of x is 19.7 and the mean of y is 216.9. So we know for a fact that the point 19.7 to 16.9 lies on our regression line, y equals 9.83x plus 23.1. You can even plug it in to verify. The second characteristic is about how the line relates to the data points. The regression line acts as a balance line. It separates the data points so that roughly half of them are above the line and half are below it. It's the line that comes closest to all points simultaneously. Now, let's shift our focus to the correlation coefficient, R. We know R ranges from -1 to 1, but let's put some more descriptive labels on those values. We can characterize the correlation strength based on the absolute value of R. A value between 0.75 and 1 indicates a strong correlation. Between 0.5 and 0.75 is moderate. Between 0.25 and 0.5 is weak. And anything from 0 to 0.25 is considered very weak or no correlation. The sign of R, positive or negative, simply tells us the direction of the slope. To really understand this, it's best to see some examples. In our next scenes, we'll look at several data sets to see how the scatter plot, the R value, and the regression line all connect. To recap this section, we've learned that the regression line passes through the mean point and balances the data. And we've established a scale for interpreting the strength of the correlation. Welcome back. To truly grasp the meaning of the correlation coefficient, let's look at some clear characteristic cases. Our objective is to visualize and compare perfect and strong correlations. We'll start with the most extreme case, a perfect positive correlation. Consider this data. When we plot these points, we see they fall perfectly on a single straight line that goes up from left to right. For this data, the correlation coefficient R is exactly 1. This signifies a perfect positive linear relationship. The regression line is y equals 2x, and every single data point lies on this line. Now for the opposite extreme, a perfect negative correlation. In this case, as x increases, y decreases in a perfectly predictable way. The points again form a perfect straight line, but this time it slopes downwards. Here, the correlation coefficient R is exactly -1. This is a perfect negative linear relationship. The regression line y minus 2x plus 12 passes through every point. Perfect correlations are rare in the real world. It's more common to have data that's a bit messy. Let's slightly modify our data. Look at this scatter plot. The points still clearly follow an upward trend, but they don't fall on a single line. There's some scatter or noise. For this data, the R value is 0.98. It's very close to 1, so we call this a strong positive correlation. The regression line y equals 2.1x minus 0.3 represents the best possible fit, even though it doesn't hit every point. Let's see the negative equivalent. Similarly, these points show a clear downward trend, but with some deviation from a perfect line. The correlation coefficient is -0.98, indicating a strong negative correlation. The regression line captures this strong downward trend. By comparing these examples, you can see the difference between a perfect relationship and a strong but imperfect one. We've seen perfect and strong correlations. Now let's look at a final extreme case. Our objective here is to understand what a scatter plot with no linear correlation looks like. What happens when there is no linear relationship between the variables at all? Take a look at this data and its scatter plot. The points seem to be scattered randomly. There is no clear upward or downward trend. Knowing the value of x doesn't seem to help you predict the value of y. Let's see what the calculator tells us. For this data set, the correlation coefficient R is exactly 0. This confirms our visual inspection. There is no linear correlation between x and y. So, what does the line of best fit look like in this situation? The regression line is y equals 5. This is a perfectly horizontal line. What is the significance of the number 5? If you calculate the mean of the y values 8, 2, 5, 2, and 8, you'll find that the mean, ugueo, is exactly 5. When there is no correlation, the regression line is simply a horizontal line at the mean of y. This makes intuitive sense. If x gives us no information to predict y, our best guess for y, regardless of the x value, is simply the average value of y. Today, we have covered the fundamentals of linear regression. We learned how to visualize paired data with scatter plots, how to quantify the relationship with the correlation coefficient R, and how to model it with a regression line. We saw how to calculate these values with a GDC and use them for prediction, distinguishing between interpolation and extrapolation. Finally, we visualized the entire spectrum of correlation, from perfect to strong to none at all. This is a powerful set of tools for analyzing data and understanding the world around us. Thank you.